All right. I mean, sometimes I realize we're going too fast, and then I look where we are and where I want us to be. Even though we teach 3 times a week, and there's way too much stuff to be covered. Okay, and so I would be disappointed to leave topics that you may be interested out of the class because we don't have time. So let me do the following thing. I'm going to try to finish a little bit about Probit regression. So we cover at least the whole topic of classification models. And then I want to generalize by discussing some concepts related with the exponential family distributions and generalized models. So the second part of the lecture may be a little bit tense, okay? And I will not cover everything. Some of you may have already heard this from earlier courses. All right, so let me see what we did is, remember we are talking about classification, so this is the posterior for being in class 1. Alpha here is W transpose phi. Phi is some transformation of the input, and F is the activation function. And we already saw in the discriminative at this setting the cases where F is a sigmoid, F is a softmax function, and we even discussed cases that lead to the same sort of outcomes in the context of generative models. But right now we're really interested to start directly from this. And so the question that we need to pose here, is there anything beyond sigmoids and softmax functions? And the idea is yes, there is. And that's where the Probit model comes. So let's see what the Probit model is. We define a threshold theta that is drawn from some known distribution P of theta. And we set the target to be class 1 if AN is greater or equal to theta, otherwise it's class 0. It's as simple as that, all right? So we're going to try to put this down in some mathematical sense. Again, the rule is class 1 if AN for a given point phi n is greater than the threshold theta, where theta is sampled from P of theta, otherwise it's 0. So effectively, the posterior probability given phi for being in class 1 is the same as the probability of theta being less or equal to AN, which is W transpose phi. Okay, I don't show here the index n for the point, so it's an arbitrary point. Okay, so the posterior is the probability of theta being less or equal to W transpose phi, which we call it A. So we can write this as the integral from minus infinity to A. So immediately you can see that the activation function here F is nothing else but the CDF of P of theta. And that's exactly where the Probit model is. Now, we're going to have to wait maybe 1 hour to show you why this is a little bit more powerful than using the sigmoid function, okay? Because we summarize it like that, but somehow this formalism that you can see here, we can generalize it with latent variables, and that can allow us to do more complex problems using this Probit model. But for now, this is what we have, okay? So P of theta can be any distribution. So here you see a Gaussian mixture, and then the CDF looks like this, and this is going to be our activation function. You may extrapolate, right, that there is nothing new here because the CDF of this, if you take P of theta to be a Gaussian, a standard Gaussian here, you remember a good approximation of the sigmoid is to use the CDF of a Gaussian with some appropriate value of lambda to match the slopes. So you may extrapolate that there is nothing new here, but trust me, the behavior of the two models is very much different, and the Probit model leads to ideas that can be generalized to more complex problems than the ones we see here. All right, so let me go directly to the training of the model. So doing sort of maximum likelihood estimation, the way we have seen for these the previous models. So what we have again is we have a data set of n points. This is our loss function. How do we call this loss function? Remind me? Cross entropy, all right? So that's the cross entropy loss function. Again, TR labels 0 or 1, and Y1 is our model, it's the posterior probability. So if you take derivative with respect to Y, if you know how to differentiate logs, basically you get that the error function derivative with respect to Yn is equal to that. Remember now, we need to compute the parameters, and the parameters here are W, where W comes in the definition, where is it? W comes in the definition of A, which is W transpose phi, okay? So, so effectively, to find the gradients of this cross entropy loss function, we have to take derivatives with respect to Y, derivatives of Y with respect to A. What's the derivative of Y with respect to A? You remember, if Y is the CDF of a Gaussian, of a standard Gaussian, do you agree that this is del Y del AN? Right? So that's what you see here. And then we have to take the derivative of AN with respect to W, and what is that? Is phi n. All right? So the gradient of the error function, of the loss function here with respect to AN, it's easily to calculate. And obviously, we're going to have to take one more derivative to find the Hessian, so we can do the Newton method, this iterative reweighted least squares technique. So again, this is a function of W because Y is a function of W, and then of course AN is a function of W. So what you do is you take derivatives of this with respect to Y, then the Y with respect to A, and then the A with respect to phi, plus whatever other terms you had, and you do the same thing for this term, and then you plug in everything together, and you get the Hessian. So basically, for the Probit regression model, everything you need to know, first derivative, second order derivatives, you know them analytically, so you can, the iterative reweighted least squares method will work nicely. All right. There is a bunch of slides at the end of this lecture that somehow they require the topic that I'm going to discuss next. But I thought maybe, you know what, you should hear these few slides, even if you don't understand them, because the notation in these few slides is slightly different from the more general notation that is going to follow. Okay? So again, I'm going to throw you some concepts that I'm going to try to justify later today in the lecture, but I want to finish this topic even if you don't follow completely everything, okay? So let me discuss, we're interested to generalize all of these models, and let's see some common features that these models had, okay? So you remember this was the error function we used for regression, right? So when you do L2 minimization, you have something like that. And I remind you, when we try to use stochastic optimization, updating the parameters W1 data point at a time, the correction that we were getting to the old parameters was basically nothing else but the error Yn minus Tn times the future vector phi n. You remember that? I mean, everything comes as the error times the future vector phi n, or, if there is no transformation, just xn. All right? So when we did MLE for linear regression models, that's what we got. We got Yn minus Tn times phi n. Now, it comes out that when we try to use the logistic sigmoid for classification, and with a cross entropy loss function, or when we try to use multi-class classification using this softmax activation function, actually the update of the parameters W was also of the same form, was Y minus T times phi n. And as I told you, it's not an accident of nature that always the updates, this gradient, basically the contribution from each point to the gradient comes to be yn minus tn times phi n. So if it is general result, can we generalize this result? So maybe we can come up with a more complex analysis. All right. As I told you, I'm going to go very briefly through this, finish a few slides, so you see the notation, and I'm going to come back and redo this with in a more abstract notation. Okay? So I just want to cover sort of the application of this exponential family of distributions to classification, and then sort of generalize from there. All right, so what I'm going to start telling you, and we will see this in the next lecture, is there is a general class of distributions that looks like this, and we call this the exponential family of distributions. The only thing that it may be new for some of you who have seen this before is that I scale this distribution with S, okay, where usually S is taken to be sigma squared, the variance basically, okay? There is a reason you do the scaling because the results basically are simplified when this distribution applies to Gaussians. And I will do these examples basically in about 20 minutes or so from now, okay? So for now, let's call a distribution that looks like this to be the exponential family of distributions, okay? And I'm going to apply this distribution not for the input vector x, but I'm going to apply this distribution for the target t, all right? So in our case, the target t, right, was basically the posterior labels in the context of classification. So given this parameter theta and given this scaling coefficient s, the family of exponential, the exponential family of distributions is written like that. Okay? These parameters theta are called natural parameters. The only thing I'm going to say at this point is that the parameterization that we see of the distribution written like that is not the parameterization you usually see in the books where the coefficients and the parameters coming have to do with the mean and the variance of the distribution. This has nothing, this parameterization, this theta, it may depend on the mean and the variance, but it's not the mean, it's not the variance, right? They're what is called natural parameters. So remember, there is an exponential here, right? There is another function of theta, and then some function of t, okay? And so let's see what happens. Again, if you don't get it, I am going to redo this example in a very general setting on the next lecture. So let me try to explain what is going on. So for this family of distributions, there is a fundamental result, okay, and I will prove it later today in the lecture, that says that if you take minus the gradient of log of g, this gives you the expectation of u. And what is u, by the way, in this problem? U is the sufficient statistics of, I write this for this distribution, right? So eta transpose u. So what is u on this, on our setting for the target values? It's t over s, basically. Okay? So effectively, if I apply this result, y, which is the expectation of t given eta, it is minus s times the derivative with respect to eta of log of g of eta. Okay? So remember, this is the you know, at each, if you look at each location x, right? This is sort of the, let's say in the context of regression, at each x, this gives you the conditional mean. In the context of classification, given an x, it gives you basically the condition, this posterior probability of t, and the posterior probability of t, isn't it the same as the expectation of t? Because t is binary, 0 and 1. You remember when we're doing classification, right? We're saying p of t equal to 1 given x is equal to this function y, okay? So isn't it that the same as the expectation of t? What's the expectation? The value 1 times the posterior times the value 0 times the other posterior, all right? So in classification, the expectation is the same as this posterior probability. So I want you to look at this equation again, and I will revisit this, and I will prove this. Okay, so hold your breath until I finish these 2 slides. This says basically that the mean, all right, is this complex function of the natural parameter theta. Okay, so the mean here I denoted with y, all right? So when we were doing classification, we had the posterior equal to some function y, okay? And this is what's indicated here. So let me explain the schematic. You give an input point x, we have the weights w, and you remember we defined w transpose x, right? We took some weighted average of the x's, that's A, W transpose X, okay? So the model applies an activation function on W transpose X. You remember, this is what we did with logistic regression. So for logistic regression, F is what function? The sigmoid, all right? So in the Probit model was the CDF of the normal Gaussian, okay? So we apply some activation function on W transpose X, and we get, what do we get? What is the physical meaning of Y, as I said here? We actually get the mean of the distribution, all right? The conditional mean, all right? So Y, it is really the conditional mean. That was the case when we were doing regression. That's the case also in the quantities of classification, because in classification, this is the posterior probability of being in class 1, which is the same as this expectation. All right, so both in classification or regression, we have Wx, we get W transpose X, some activation function, we get the mean, the conditional mean for every x. And now look carefully at this equation. If this equation is true, I have not proved that equation, but trust me, for this family of distributions, this is a very general result. This equation tells you that y, it's a function of eta. So we will show, when we do this rigorously, that this equation is invertible. That actually, you can also write eta as a function of y. In other ways, given the conditional mean, there is a function that will actually take you from y to eta. And the reverse is true. There is a function that will take you from eta to y. Okay? And now, this function psi that you see here, all right, it depends on the particular family of the distributions that we work with. So for a particular function, you know, the particular family of exponential distributions, this psi is given. And I will give you many, many examples in the lecture today. Okay? So think of this psi, it's part of the family of distributions, it's given. All right? And uniquely takes the conditional mean to the natural parameter theta. Now you may say, why do I care about all of these things? Well, let me do a calculation for you, and you will see why, what is there that is going to allow us to generalize our results and see that they're applicable actually for any distribution from the exponential family. Remember, if I take the target t to be from the exponential family, is this basically the likelihood, the log likelihood? Look at this result there, all right? And tell me if this looks fine to you. Again, I see log of g's. So there is one eta for each point n. Can you tell me why there is one eta for each point n? Because when I write this distribution, this is really not the distribution of t alone. This is the conditional distribution of t given x. So the natural parameter theta change when x changes. So effectively what I have is summation of the logs of g of eta n, and then from the exponential I have eta n times tn divided by this scaling s. Okay, it looks like that. Now, let me see where the general result comes. Let's take derivatives of this, with respect to the parameters w, right? Because we were generalizing the stochastic optimization algorithm. So if you take derivatives, you have summation over all the data points, the derivative of the log of g, and then this is Tn over S. So this is derivative with respect to eta, and then eta would be derivative with respect to y, and then y with respect to alpha, and then derivative of alpha with respect to w. You see that? Basically what I do, right, if you think, I take derivatives with respect to eta, derivatives of eta with respect to y, of y with respect to a with respect to w. Okay? The derivative of an is phi n, and this is the very general expression that you get when you try to compute the gradient. All right. Here is where the generalization comes if you get it with these slides. If not, you will see an extensive new talk, a new presentation coming after this slide. This activation function that we have used up to now, it was, we said let's use a sigmoid, let's use a softmax function, let's use, the CDF of the Gaussian. Well, how about if you, for a given family of distributions, this exponential family of distributions, if we select the function f to be such that this product is equal to 1. Will you agree that immediately if this by an accident of nature comes to be equal to 1, that somehow what you get is the error times phi n, which is the general result, and again, divided by s just to simplify the algebra. All right? But if this thing comes to be equal to 1, then we get this very general result, but this result will be applicable not just for the sigmoid, not just for this function or that, it will be for everything that comes out from this exponential family. So the question is, how do we select f so that this thing becomes equal to 1? I am going to not give you all the details, all right? Just the facts, actually, and then we will revisit this in fine detail on the next lecture. So here is what you need to do. This psi is defined by the exponential family that you're using. So it's given, all right? For a given exponential family, psi is given. So let's do the following simplification. Let's somehow select f. So a is equal to eta. A is equal to eta. Remind me, what is a? What's the definition of a? W transpose x. And what is eta? Are the natural parameters in the distribution that are unique to every family of distributions. So we're going to make a equal to eta. If you think, right, so a is equal to eta, you know what it means? From y I can go to a with what transformation? F inverse. And from y I can go to eta through psi. So F inverse has to be equal to psi. All right? F inverse has to be equal to psi, which is what you see here. And when you rearrange this equation, you can actually immediately see that this function psi computed at y, all right, times f prime computed at psi is equal to 1, and the derivative term that I mentioned before, this product becomes equal to 1, and you get this very general result that is applied to many different distributions from the exponential family. All right? So when you say it, sometimes people don't even bother to prove anything because they know this result is true. I mean, if you use a likelihood from the exponential family, you can just write this result and it's ready to go. And hopefully now you appreciate the importance of stochastic optimization, Robbins-Monroe, because that's the structure that you get when you do Robbins-Monroe. Okay? So, so I gave you lots of things for thought, right? That somehow we can generalize these results for the exponential family. And I told you out of nowhere what an exponential family is. And you understood about 5% of that. So now we have to go back and understand the other 95% if my computer behaves. Let me see. I don't see the mouse moving. Do you see the mouse on the screen? Yes. All right. Where do I have to go? how do we get, okay, here it is, good. All right. All right. All right, so now we have the luxury to go back and actually learn these things slowly and see all of these general results, okay? So what we need to discuss is some of the fundamentals of generalized linear models. If you check in statistics departments, I don't know about if we have a class like that at Notre Dame, but it's usually a required class for statisticians to take a course on generalized linear models, just on that subject alone. So we will cover it only in half an hour, right? But it's an enormous subject and extremely fundamental to many aspects of statistics and machine learning. So what type of distributions are in the exponential family? You know, I wrote some here: Bernoulli, beta, binomial, chi-squared, Dirichlet, gamma, Gaussian, geometric, multinomial, Poisson, etc. You know, things like the Cauchy distribution, student T, Laplace. If you have a mixture of Gaussians, even the uniform distribution are not in the exponential family. If you go to Wikipedia and you type exponential family, you will actually get a very nice table that gives you all the information about all the distributions that are in the exponential family. So in this set of nodes, I am going to assume that the conditional distribution of y given x is in the exponential family. So this is sort of supervised learning, right? So either you do regression or classification. So I'm really looking at the conditional distribution of y given x. So in some of the slides, the x may be hidden, but I want you to remember everything is about the conditional distribution. When I say I'm going to have a generalized linear model, I'm referring to this conditional distribution of p of y given x. So what is the general form of the exponential family? Is this equation that you see on the top. There's no scaling here. This is sort of the most primitive fundamental form of this distribution. And there is a notation here that you need to learn because it has lots of implications, not just in this lecture, but everywhere else. So I'm going to define a of eta to be minus log of g. So that way you can put g in the exponential. All right, so you have eta transpose u minus a of eta. So remember this, a of eta equal minus log of g. Now, you can appreciate that this function g of eta, and by extension a of eta, what they do is they normalize the distribution. Because if you take an integral of this over the space of x, right, you're going to get g of eta times the integral of h times this exponential that has to be equal to 1. So g of eta is the normalization factor of this distribution. Okay? G of eta is the normalization factor. The normalization factor z, you can write it explicitly as 1 over g. All right? 1 over g. And using the definition of a being minus log of g, you can see a is log of zeta. Okay? Z comes with different names. A name you may see in statistics and statistical mechanics is the partition function. Okay? So if you write the distribution in terms of z, it looks like this. Okay, so I just put g equal 1 over z. Okay? These are the natural parameters. Okay? U of x is called sufficient statistics. The word may already resonate to you. We will explain what U of x is called sufficient statistics. And z is the normalization factor. It's called the partition function as well. And you can notice z is a miserable term because if you look at, for example, even a of eta, okay, equal to log of z, log of z is this integral, all right? So what you have is log, integration, and exponential. Very complicated term. And this is an integral over the whole space of x, all right? So this is, has the complication that things like these, the model evidence has, right? But in the context, at least, of statistical calculations, z is very much related with the free energy of the system. Okay, and you can extrapolate that basically everything for this particular distribution depends on z at the end of the day. So it's extremely important somehow to be able to do this type of calculations. All right? Sometimes these natural parameters theta depend on some other parameters theta, okay? And so theta is, basically whatever parameters you see in a distribution that is part of the exponential family. But I really want you to concentrate not on the theta, but on the eta, okay? So this is the natural form, okay? And the only thing I can tell you right now, until you see the examples, these parameters theta are not the parameters you see. Like, for example, when we do the Gaussian distribution, eta is not going to be the mean and the variance. Have nothing to do with the mean and the variance. I mean, have to do something with the mean and the variance, but they're not the mean and the variance. Okay? So they are natural parameters. So, for example, if you write something like that, you can say eta is a function of the mean and the variance. So those are the theta parameters, but that's not what we will use in this lecture. I am not going to go through the slide because it requires some advanced knowledge from probabilistic graphical models. I am only going to give you the conclusion because it's very important. If you have a distribution over discrete random variables, automatically it's in the exponential family. So if you give me any distribution of discrete random variables, this slide proves basically, with some abstraction, that that distribution is in the exponential family. I'm not going to give you the proof, but you can. The slide actually has a lot of the details. You can read it. So let's do some trivial examples. I stated that the Bernoulli distribution is in the exponential family, so the question is why? You remember the Bernoulli distribution? This is the coin example, right? So x can be 0 or 1, heads or tails. Mu is the probability of getting heads, okay? So you agree that the Bernoulli distribution is this, right? So let's do the following thing. The trick here you have to think is we have to create an exponential. And to create an exponential, think of taking the log of the distribution and then exponentiating the log. So if you take the log of this, what do you get? X log of mu plus 1 minus x log of 1 minus mu, and then take exponential. All right? So you do this trick, and you rearrange the exponential. Here you get 1 times log of 1 minus mu alone in the exponential, so you can pull this outside. So this is what you get. So will you agree with me immediately that the natural parameters for the Bernoulli distribution, the parameter eta is log of mu divided by 1 minus mu, and that g of eta is 1 minus mu. So this function here that you see is called basically the logit function, okay? And it comes out that this function is invertible. So you can see here I can solve mu as a function of eta, and the inverse function of the logit function, by miracle of nature again, comes to be the logistic sigmoid, not an axiom. Okay? So again, this is the logit function, and this is the logistic sigmoid. What I'm more interested is two things here. That we computed this to be in the exponential family, we computed eta, and we conclude from this simple calculation that from eta, we can go to mu. And what is mu here? What is with words, what is mu? What is the mean of the Bernoulli distribution? Takes values 0 and 1 with probability mu. So what is the mean? Mu. So effectively what I want you to remember is from eta, from mu we can go to eta, and from eta we can go to mu. It's invertible. In other ways, if you know the natural parameters, you can actually compute the moments, and if you know the moments, you can compute the natural parameters. This is very important, and the result is very general for the exponential family. What is the sufficient statistics here? It's just x, all right? You remember here we're supposed to have eta transpose u of x. So u of x is really equal to x, and if you really want to be precise, it's not really x, it's the indicator function that x equal to 1. Right, so the sufficient statistics is this. The h of x, there's nothing there, it's 1. Okay, and a of theta is minus log of g, and g is 1 minus mu, or if you write it in terms of theta, you get something like this. I'm going to be using these results, right? But now we have seen that the Bernoulli distribution can be written in the exponential family, and we have not only, so this is the moment parametrization. This is written in terms of moments. This, if you define this g of theta, and if you define this as zeta, log, this log is equal to eta, so you have exponential of theta times x. So this parametrization in terms of theta, right, is the natural parametrization of the distribution. This is the moment parametrization. By the way, the natural parametrization, in most cases, it would be more complex than the moment parametrization. But something more complex can be more useful than something less complex, and we will take advantage of that. So let's do another example. The Poisson distribution, I remind you, is like that. So remember the trick, you have to create the exponential. How do you do it? You take the logs and then the exponential. So forget the factorial there, okay? That's a function of x. So you take the log, so you have x log of lambda minus lambda, and then you take the exponential. So immediately you can see that the sufficient statistics is x, the natural parameters is log of lambda, and a of theta actually in this case, you can immediately see that it's lambda. All right, so it fits directly in this exponential family of distributions. And what is the mean of the Poisson distribution? Anybody remembers? What is it? Lambda. So the mean is lambda. So what does this equation say? That given eta, all right, I can go back to moments and compute the mean directly. Okay? And the variance is also lambda, right? Okay, so we are basically set. The idea here is that, from the natural coordinates, we can go to moment coordinates and the other way around. This is very, very important. All right, so let me do something that it's a little bit more complex. So let me use the multinomial distribution. So remember here I have a variable x that I can assign it to m bins, all right? And I can assign it to each bin with probability mu1, mu2, mu capital M. And xk will be either 1 or 0. So either occupy the k bin or I don't occupy it, okay? And so this distribution, it also belongs to the exponential family, but when you try to prove it, you find out that things look a little bit complicated. Okay, so let's see why. What do? We take the log, the product becomes summation, and then I have xk log of mu k, and when I'm done, I take the exponential. So somebody will say done. P of x of, this is originally the moment parametrization, and now you say I'm done. This is the natural parametrization. The parameters theta in this case are what? This is a vector of log of mu1, log of mu2, etc. All right? So you say you're done. But can you tell me what is the normalization factor of this distribution? What is A of theta? You remember in the exponential family, right? I see there, A of theta has to do with the normalization factor. So how much is A of theta here? Where is 1? I don't see 1. I mean, I'm looking there. How much is A of theta? 0. That's not good news. I mean, if we cannot normalize the distribution, it's not a valid distribution. And actually, on the first slide, I wrote on the bottom, right, that the normalization, that the integral has to be finite. So we have a problem. But it's a problem easy to solve. Why it's an easy to solve? because you know what, there is a nice constraint that says this probability that this mu k's are not independent of each other, that if you sum them up, you should get equal to 1, right? The probability that you will be in one of the bins has to be equal to 1, okay? So what you can do is, when you took that exponential that we work with, you split it in 2 terms. You split it on a summation from 1 to m minus 1, and then you write the last term as, so we're going to have log of mu capital M, which is 1 minus this. You agree? But I also have written x subscript capital M as 1 minus this x's. Is that okay also? I mean, in every bin either occupied or not, right? But when I sum the x's over all the bins, I also get 1. Only one of those is 1, okay? So basically I have this plus 1 minus that times this log, okay? I am not going to bother you with all the algebra, but now you can you actually see that I see something that looks like the natural parameters times x, but the x's are going from 1 to m minus 1, and then suddenly I see a partition function there. I mean, I see an a of theta there, which is not 0 anymore, all right? So let me just, I'm going to give you the final results because the rest is algebra that you can very easily follow. It comes out that the natural parameters basically are eta k equal to log of mu k divided by 1 minus this summation. And actually this summation, you can call it mu capital M, all right? Okay? And you can define arbitrarily, since this goes from 1 to m minus 1, you can define eta of capital mu to be equal to 0, all right? I mean, you can immediately see according to this definition, right? If you put k equal capital mu, you get log of 1 equal to 0. All right, so that's our natural parameters. And you can show with playing with the summations and reversing the equation that if you know the natural parameters, you can actually invert this equation and go from eta to mu. And surprise, surprise, when you go from eta to mu, what function do you get? The softmax function. Again, is that an accident? You tell me. All right? You go suddenly from eta to mu, and what you get is the softmax function. Let me just give you all the results, right? The distribution looks, so we define what the etas are. So it's exponential of eta transpose x. There is this g of eta here, that is what you see here, okay? And, all right, and a minus log of g, you can write it this either, you know, there's a minus sign there, either this log, all right, or you remember the n subscript capital mu was, how much was it? It was equal to 0, so the exponential of 0 is 1, so you can actually write this summation here, summation from 1 to m, where you also incorporate eta capital mu. Okay, so this is sort of a compact way to put everything together. All right, done. So this was a little bit more intensive. I don't have to go through the beta distribution. It's trivial. Basically, you can immediately show that it fits in this form. And these are the sufficient statistics, the natural parameters, and the function A. The same thing about the gamma distribution. It takes no effort. You take logs, then exponential, and immediately you see what the results are. So when we need, we will come back to the slides and use them. Let's do the Gaussian, all right, because everybody's familiar with the Gaussian. So the Gaussian, we are familiar with the moment parameterization. That's the moment parameterization. So the question is, can I write this in terms of natural parameter theta? Is the Gaussian the exponential family? Obviously, it should be in the exponential family because this exponential is screaming and say, you know, that's me, exponential family. Okay? So let me just give you the results. When you expand this and you try to put it on this form, it comes out that the natural parameter theta is a vector, because, you know, I mean, you can appreciate, right? We have two variables here, mean and variance, so there will be two etas. So eta 1 is mu over sigma squared, eta 2 is minus 1 over 2 sigma squared, and A of eta, all right, is given by this very nice looking function, okay? Don't panic, this is how it looks like. And the statistics, the sufficient statistics, is basically x and x squared. By the way, on the previous lecture at the end of the slide that I was way ahead of myself, you remember that I put a 1 over s, some scaling on the exponential family. You know what the purpose of that scaling was? So when I write the natural parameters for the Gaussian, I don't get mu over sigma squared, I just get mu. If you don't put that s being equal to sigma squared, what is going to happen, right, when you compute the mean, when you compute the natural parameter eta, the first term is going to be mu over sigma squared, and it would be nice if it is just mu. Okay? Because it will it simplifies the algebra in the context of eta. It makes some of the equations tricky, so you basically have to look carefully if you do some scaling. If you do no scaling, you get mu over sigma squared minus 1 over 2 sigma squared. We don't need this. You may say, can I do this trick now with this natural parameterization? Can I do this for a multivariate Gaussian? And it's actually straightforward, right? But you need sort of to use a little bit your imagination. So if I take the exponential in a multivariate Gaussian and I expand the exponential, right? Lambda is the precision matrix here. So you get a quadratic term in x, a linear term, and then this constant term, okay? So what we need to do is we need to put the distribution on this form. So what we need is, we need some vector eta transposed with some sufficient statistics of x, some functions of x, okay? What functions of x do I have here in this equation? To define a multivariate Gaussian, I need to know x and what else? X transpose, okay? So what you need to do is, all right, you define u of x to be x and minus the vectorized form of the matrix x transpose. Right? You can take every column, put it together in a long vector with minus 1/2, and u of x is x and minus 1/2 of that. And then you can immediately see the zeta transpose u. It's obvious because x here is inner product with mu transpose lambda. So what you do is you define the natural parameter to be xi, for xi is lambda times mu. All right? You can see from there, xi is equal to lambda times mu. And from the first term, because you had an inner product between x transpose and lambda, you need to have eta to be the vector version of this precision matrix lambda. Everybody can see that? So for the multivariate Gaussian, it looks complicated. It takes this nice form. All right. So let's prove this result that I used at the end of the previous the slides of the previous lecture. A very fundamental result that is unique to this exponential family of distributions. And this result says, this is what we're going to prove, that if you take the gradient of this function a with respect to eta, this gradient comes to be the expectation of the sufficient statistics u of x. I keep calling u of x sufficient statistics. I will come back to what that means, right? But somehow is, what functions of the data of x do I need to describe this distribution? And what I need is some function u of x, like in the Gaussian, I need x and x squared. That's what u of x is. But this result says, if you want to calculate the exact expectation of the u of x, what you need to do is, you simply need to differentiate the function a with respect to the natural parameter theta. Okay? A wonderful result. How do you derive this result? Well, if these distributions are normalized, right, the way we define them, this integral is equal to 1, and this is what the distribution is. So let's do the following thing. We are going to plug in the definition of the exponential family inside that integral and take derivatives with respect to eta. Would you agree that you will get one derivative from this term, which is here, and then you will get another derivative from here, which is u, times the exponential? And this, because we took derivative with respect to g, this is not exactly our distribution, so what we will do is divide by g and multiply by g. If we multiply by g, g times the integral is equal to what? Is equal to 1 from the normalization of the distribution, all right? And when you take this on the other side, you get minus gradient of g over g equal to g times h, the exponential times u. And what is g times h times the exponential? Is my distribution. So when you take your distribution u of x dx, what do you get? The expectation. And I can simplify minus gradient of g over g using the partition function zeta, or even better, alpha. So alpha is minus log of g, all right? So this gradient here is the gradient of a with respect to it. So it comes out exactly for this exponential family that the gradient of a with respect to the natural parameters is the expectation of the sufficient statistics. Be careful, and maybe if I find time, I will let this explicit in the slides. When you do the parameterization, you put the scaling coefficient s, this equation has to change, right? Needs to include an s term there, okay? But that derivation basically comes straight in a straightforward manner from here, okay? So for this general form, this is true. We can push actually this result to higher order derivatives. So I am not going to do the derivation. I am just going to tell you that if you take the second derivative of a with respect to eta, surprise, surprise, it comes to be equal to the covariance of u of x. Okay? And this result is not only useful because it allows you to calculate exactly the covariance of x, but is more useful because it already tells you by the definition of the covariance, which is a positive definite matrix, that this function a is a convex function. All right? And does anybody care that this function is a convex function? Yeah, I care about the fact that this function is a convex function because when you look at the gradient of a versus the parameter eta, it looks like this. All right? And you know what that means is there is one-to-one mapping between eta and the gradient of a. But the gradient of a is equal to what? According to our calculation before. The expectation. So there is one-to-one relation between eta and the moments of the distribution. You see that? So for example, if you are interested on the mean, the fact that this is a convex function tells you, you know, one-to-one relation between eta and the gradient of a. All right, that's this function, how it looks like. Okay, but the gradient is equal to the expectation, so there is one-to-one relation between eta and the moments mu, and so we are going to take advantage of that fundamental result shortly. If you want to see these relations in action, all right, you can take any of the examples that I gave you for the distributions. So if you do this for the univariate Gaussian, and you take derivatives of, so A, I gave you the formula, all right, before. This is, it looks like this. If you take derivatives with respect to eta 1, the result indeed comes when you plug in what eta 1 and eta 2 is. You come in exactly that you get the expectation of x. If you take derivative with respect to eta 2, you know what? You will get the expectation of what? Of x squared. Right? Because eta is a vector. All right? And you remember we said the expectation, I mean, the gradient of A is the expectation of u, but u is a vector. So the expectation of x squared would be the derivative of A with respect to eta 2. So it comes out, this derivative is mu squared plus sigma squared, which indeed, isn't it, the expectation of x squared? Similarly, if you take derivatives with respect to eta 1, you get sigma squared, with the variance, etc., etc. All right, so let me tell you why we call u of x sufficient statistics, okay, in case you have not seen it. These concepts may be a little bit new to you, so what I suggest is use a common sense understanding of this. You don't need to understand any of these graphs or the equations, but you know, if you understand what this the sort of the common sense interpretation that I'm going to give, we're just fine. So think of this graph where x is here, u of x is here, and theta is there, and these directions of the arrows basically tell us that u of x, you know, is related with x, all right, and the relation is going this way. If I know x, I know u of x. If I know u of x, I know theta, sort of, okay? For those who know something about probabilistic graphical models, they will notice from this directed graph, okay, that the parameters theta, okay, should actually use here, you can think theta and eta is the same thing. I don't know how the theta came on this plot, all right? Maybe by copying this plot from Jordan's book. So it doesn't matter, right? So these are our natural parameters. So think from this graph that somehow theta is independent of x given u of x, okay? And what you see here is, you see this is actually the equation you should concentrate. That if I know u of x, all right, if I know u of x, then this distribution is independent of x, which means that condition on u and x, right, is the same as if I condition only on u. Which means that u of x contains all the information in x that is needed to define what theta is. So let me say it again, that u of x contains all the information that you need to know about x that is required to compute the parameters of your distribution. So do you appreciate now why we call it sufficient statistics, right? So you can think, right, when you do an MLE of a Gaussian, and I give you lots of data, x1, x2, xn, what are the sufficient statistics for computing the MLE? What combination of the data do you need to find the mean for a Gaussian? What's the MLE of a Gaussian? The empirical mean. So what's the sufficient statistics? Sum of xi, right? That's empirical statistics. That's exactly, I mean, the same concept we're talking here, okay? So when you look at the dependencies in this way, you can think that given u of x, and that's why this circle is drawn dark, given u of x, theta is independent of x, okay? So given u of x, theta is independent of x. You can actually reverse the arrows to make it more interesting. And let's look at this equation. What does it say? That given u of x, x is independent of theta. How do you understand that? Given u of x, all right, x is independent of theta. Before we said the only information you need to compute theta is u of x. Now, when you look at this equation, what does it say? That all the information contained in theta is contained where? In u of x. The other way around, all right? And again, this has, reversing the errors has implications, right? But at the end of the day, you get the same result. And actually, if you remove the errors at all completely and you do an undirected graph and you try to decompose the joint distribution of u of x, and theta, it comes out, and again, I'm not going to go through all the algebra here, that effectively this distribution can be factorized as a product of one distribution that involves x and u of x, and another distribution that involves u of x and theta, exactly the same way as you get when we wrote down what the exponential family of distributions is all about. So in some sense, there is sort of a generalization of this thing here, and this whole thing goes under the name of this Niemann factorization theorem, that sort of starting with conditional independence relations and the definition of sufficient statistics, you actually can derive the dependencies, if you like, of the different terms here, but obviously you cannot derive the fact that there is an exponential here, right? That's particular to the exponential family, but you can derive that you have a function that involves only u and theta, all right? And there's a function that involves only u and x, u of x and x. All right, let's continue. So so we have the exponential family of distributions. There can be many different distributions. So let's do an MLE estimate for a distribution that's in the exponential family. So you throw at me a bunch of data, x1 to xn, all right? So the sufficient statistics, basically we have u of x, this summation of the u of x ones. So would you agree with me that the likelihood looks like what I have here? You remember h of xn, so I'm going to have a product of this. Then I'm going to have the normalization factor to the power n, okay? And I'm going to have here exponential of eta transpose the summation of all the u's. By the way, not to confuse you here, when we did the last two slides of the previous lecture, I mentioned for each data point, I said there was a different eta. Here, the eta is the same, because you know what? I don't work with a conditional distribution. There's only a distribution p of x. So there's only one eta. All right? So when you work for a conditional distribution, it's different. But for one distribution, this is what you get. So if you take the logs of this, you get some summation of these factors. So you get n times log of g. Log of g is minus a. And then you get eta transpose the summation of the sufficient statistics of xn. So if you want to find the MLE estimate of the parameter theta, you have to take derivatives with respect to eta. So what's the derivative of this term? N times, what's the derivative with respect to eta of A? It's the exact moment, basically, of the sufficient statistics. All right? And so I put n on the other side, and what's the derivative of this? Is the summation of u of xn. So what you get is, you get this amazing result that it says that the empirical mean is actually matches the exact expectation of the sufficient statistics. This is what's called moment matching, okay? So at the MLE point, okay, so this is computed at the MLE, the exact expectation is equal to the empirical mean of the sufficient statistics. So effectively, you don't really have to compute eta at the MLE to compute this moment. What you do is you compute, given the data, you compute this, and then you're done. I give you an example of this for this Bernoulli distribution, but more or less you got the meaning of this. So let me, since we talked about the this thing with the MLE, let me give you a result that actually is sort of more general than the exponential family, but it's sort of an appropriate location to insert this. So let me state first the result, and then we can see if we have time to do the proof. Everybody knows what's the Kullback-Leibler distance between two distributions. So imagine that you have a distribution P of x given theta, all right? You know, as I said, can be beyond the exponential family. You have a distribution like this. And this distribution, P empirical of x, is the empirical approximation of x. So what does that mean? What's an empirical distribution approximation? For some others, you know, you may have seen it in the literature as a Monte Carlo or a sample approximation of the distribution. So what's the empirical distribution of x? If I give you n samples, how does it look like? It's 1 over n, and then you have summation of a lot of delta functions in each sample. That's the empirical distribution. So it comes out, if you take the KL distance between the actual distribution and the empirical distribution, and you try to find the parameters theta that minimize this, this problem is the same as the problem of maximizing the likelihood. All right? And I wanted to throw this slide because in the variational setting, right, and hopefully we will reach that point in this course and we'll discuss about variational methods. You know, people don't really like saying, oh, I maximize the likelihood because it reminds people that this is not fully Bayesian. So everybody starts, even though they maximize the likelihood, they say, no, minimize this Kullback-Leibler distance, okay? Well, but unfortunately it's the same as maximizing the likelihood. The first term comes to be minus the entropy of the empirical distribution, so it's independent of theta. And again, there is in the proof it's straightforward, so you can actually follow it. I'm just saying maximizing the likelihood, exactly the same problem as minimizing the distance of your distribution from the empirical distribution with the 2 cycles. All right. So why bother about the exponential family of distributions? Because you can write results that they are very general, and not just for one distribution, but for many distributions. And all of these results have a nice closed form solution. So one of this is you can write down the posterior distributions for parameters. You can write down the marginal likelihood, the evidence analytical. You can write down the predicted distribution, the Bayes factors. Everything can be written down analytically. Okay? So let me give you some examples to appreciate these analytical calculations. So what we have here is the exponential family of distributions, and I wrote eta as a function of theta. So you can think, you know, if you do Gaussian and eta are the natural parameters, maybe you're really interested in the moments, but I write this in terms of theta because this is sort of the format that I want to take advantage from. So what we need to do is we need to introduce some prior. So we want to compute, let's say, the posterior of the parameters theta. So what I'm going to do is I'm going to introduce a conjugate prior to this exponential family of distributions. And the conjugate prior is going, you know, you can extrapolate from this form here. It's going to have this form. G of theta to some power, that I call it mu 0, and then exponential of theta transpose tau 0, right? And why is this a conjugate prior? Because you can see if you multiply them, right, this will become mu 0 plus 1, and this will become eta transpose of u plus tau 0. You see that? So basically the distribution you will get will be back in the exponential family with updated parameters. I am going to do some rescaling of the parameters to make things really look nice. And the rescaling of the parameters, this tau 0 that you see there, I am going to write as mu 0 times tau 0 bar. Okay, mu 0 is that. So I'm going to write tau 0 to be mu 0 tau 0 bar. Definition. Why is that? Because then the prior, the exponent here can be mu 0 times tau 0 bar. And this thing, if I put it inside, becomes minus a times mu 0. And guess what now? If I multiply the two things, all right, if I take, this is my likelihood, right, for n data points. This is my prior, written in this rescaled form. if you multiply them, look what is happening here. You have eta transpose the summation of u's, and the summation of u's, I write them as n times u bar. All right? Plus n0 times tau 0. And then you have, of course, this g to a power n plus nu 0. So the physical meaning here is, right, is like I had n measurements of value u bar, and I had nu 0 prior measurements with strength tau 0 bar. You remember I mentioned earlier in the course that the exponential distribution is the only distribution family where you can assign physical meaning to the parameters of the prior. So the physical meaning, you can see it here, right? The same way you can say have n real measurements of value u bar. Here you say plus n0 prior measurements of value tau 0 bar. Bottom line, you multiply them, you look at this, it's in the exponential family with updated parameters. And what are the updated parameters? I give them to you here, all right? So nu n is nu 0 plus n, tau n bar is what you see here, and sort of we're done, all right? So the posterior, it's in the exponential family, and you know, with updated parameters are very easy to compute. You can actually do things further, and I know I maybe in passing I did this even in the course in the fall, and I remember everybody in the room that was attending the class remembers everything, right? So what we did is, look, we computed a posterior with some training data, all right? We had this training data. Now, you know what I want is, I want to find the predicted distribution of x prime new data. And you notice I don't just give you one data point, I give you a whole design matrix x prime. I say, you know, if this is my previous sufficient statistics, I want you now to give me the predictive sufficient statistics. Tell me what's the probability of observing x prime. And it comes out that the answer is analytical, because what you need to do is take the likelihood for given parameters times the posterior, integrate in the parameter space, all right? The likelihood is in the exponential family, all right? I assume here I have n, I'm interested, x prime has dimension n prime, right? So on n prime future data. So I write the likelihood as this times this to n power times this. Everybody agrees? Yes? Right, that's the prior, I mean, that's the likelihood. And then I have the posterior, and you remember the posterior I trained it with n previous data, all right? And the posterior was in the exponential family, so I'm writing it in this form here. So what you have is this normalization term there, I have this normalization term there, and then I have, if I combine all the other terms, I have g to a power n prime plus nu n, exponential of eta transpose of u of x plus tau 0 plus u of x prime. And this whole integral has an exact answer. From where is the exact answer of that integral? But we never have to compute by hand. That integral is what? It's the normalization of a distribution from the exponential family with what parameters? With sufficient statistics that look like what? U of x prime plus u of x plus tau 0. And what parameters? N prime plus nu n, and nu n is n0 plus n. Does this formula remind you anything? You know, we have the ratio of two normalization factors. Where did we see calculation of normalization factors? Evidence. Can you use this formula to compute the evidence? So we use it here to compute the predictive distribution. How do we make this to give us the evidence? Very simple. You take n equal to 0. So you don't have any previous data, right? So you know that immediately will give you the evidence. And then what the evidence will be the normalization factor of the prior times the normalization factor of the posterior times this thing coming from the likelihood. All right, very general result. 1:45, and I think the light is going to turn off on me, so I don't want to even think of going to the next slide. I was hoping to finish this. We have another maybe 30 slides, so we will cover them tomorrow, and we will move to new topics next week.